A very good morning to all of you. So in the today's class, we are going to discuss about the differences between the perfect gases and the real gases of this engineering thermodynamics course. That is, under what conditions we are able to call it a gas as a ideal gas, and similarly, under what conditions we can call it as a real gas. So these are the important things we are going to discuss in the today's class. And this topic is classified or the labeled as the self-learning topic of the lecture number 3. So the perfect and real gases. So what is the motivation? That is why we have to study the concept of the perfect and real gases. So here it is essential to know that under which conditions a gas is said to be an ideal gas or perfect gas, and similarly a real gas. So it is also having the outcome. So as usual, every lecture should have the objective as well as the outcome. So the outcome is after completion of this lecture, you should be able to distinguish the perfect gases as well as the real gases, and similarly the estimate the properties of the various gases. So with this intention, we are going ahead. So first of all, how can we define the ideal gas? So that is very important one. So ideal gas is maybe defined as it is basically satisfying the perfect gas equation of the state, that is the PV is equivalent to MRT or PV is equivalent to nRT under all conditions of the pressure and temperature. So it is known as the ideal gas equation. So the ideal gas obeys the kinetic molecular theory of the gases. So that is the basic behavior of the ideal gases. But before going to discuss about the real gases, so it is very important to know that. So how can we define the ideal gases in other forms also? That is very important one. So that is a ideal gas or perfect gas has no molecular force of attraction and there is no molecular force of repulsion among the gaseous molecules. That is very important one. That is simply we can say that most of the people will say that ideal gas is nothing but it will obey the perfect gas equation of the state, that is PV is equivalent to MRT, and they have to satisfy the various types of the laws like Boyle's law, Charles' law, Gay-Lucas law. So whenever they are satisfying all these laws, then the gas is said to be ideal. Okay, that is also true. But in addition to that, so it is very important one that, so that is the ideal gas is nothing but it should have, it is not having any molecular forces of attraction or repulsion among the gaseous molecules. Is it possible in the actual practice? No. So whenever a gas is physically existing, so definitely it should have some physical forces of attraction and repulsion among the gaseous molecules will be there. So that's why the ideal gas is a very difficult to obtain in the actual practice. So that is normally in our calculation purpose and in our books we have taken the atmosphere air is an example of the ideal gas. That is, it is closely behaving the conditions of the ideal gases. So that's why the all our calculations, all our calculations we have taken the air is an example of the ideal gas. So that is a very important one. So the second one is also very important one, that the state of a zero pressure, the state of a zero pressure of a real gas is called as the ideal state. The state of a zero pressure of an ideal gas is called as an ideal state. So what will happen at the zero pressure? So that is very important one. So that is the identical behavior of a real gas. So in the next slide I have shown you here in the real gases, that is, so in the next slide of the real gases, that is a real gas may be defined as a gas which obeys the gas laws under low pressure and high temperature. That is very important one. That is under which conditions a gas will behave like ideal gas. That is at lower pressures and at the elevated temperatures and at the higher temperatures a gas will behave like ideal gases. That is very important one. So what will happen at zero pressure and at the elevated temperature? So that is very important one. So that is at this particular the reduced pressures and at the elevated temperature values, the gas molecules are basically lie far from each other. So whenever the gas molecules are lie far apart from each other, so automatically the molecular forces of attraction or repulsion among the gaseous molecules is very small, or it may be neglected. So that is the reason why the gases will behave like the ideal gas condition at lower pressure and higher temperature. That is very important one. That is, they are basically lying very apart from each other. So whenever they are lying apart from each other, so the molecular forces of attraction or repulsion is very small among the gaseous molecules. Hence, it can be treated as an example of the ideal gas. That is the basic concept. So the real gases are nothing but which are deviating from the ideal gas behavior of the state. All those gases normally taken as example of the real gases. That is, whatever the gases which are existing physically, all those things can be considered as an example of the real gases, because I told you that ideal gas is very difficult to obtain in the actual practice. So that is the basic difference between the ideal gas and real gases. So the same thing I consolidated in this particular one. So that is the ideal gas which obeys the gas laws and the perfect gas equation of the state, that is the PV is equivalent to nRT. So that is under all pressures and temperatures, but the real gas will behave like ideal gas at lower pressures and at higher temperatures. So ideal gas is purely hypothetical. It is purely hypothetical. That is, it does not exist. It does not exist. So nitrogen, helium, hydrogen, which do not liquefy easily, come nearest to behaving as ideal gases. And the next one is all gases are real. So just now I told you like this. The another important point is volume occupied by the molecules is negligible as compared to the volume of the container. That is, as compared to the total volume of the container, we are neglecting the volume occupied by the each and individual molecule in the ideal gas concept. But whenever we are coming to the real gas concept, definitely each and individual element will occupy some amount of the volume. So the volume is to be considered in case of the real gases. And in the ideal gases, I told you that the forces of attraction or repulsion can be neglected. But in the real gases, definitely whenever there are molecules are physically presented, so there will be some attraction will be there and there will be some repulsion among the gaseous molecules are also there. So like that, we can differentiate ideal gases as well as the real gases. So the important one is, that is, when can a gas can be treated as a perfect gas. So just now I told you that at lower pressures and at the higher or the elevated temperatures, so this can be treated as a perfect gas. So lower pressure means it's the lower densities. So that is, a ideal gas is one which obeys the ideal gas equation of the state, that is the PV is equivalent to mRT. So that can be considered as an ideal gas equation of the state. So now coming to the real gases. So the van der Waals equation of the state is very important one. That is, the real gas behavior can be predicted by using the van der Waals equation of the state. So the van der Waals equation of the state is given by P plus A by V square into V minus B is equivalent to RT. So now just you compare this van der Waals equation with the ideal gas equation. Ideal gas equation says PV is equivalent to RT. But van der Waals equation says that so A by V square term is added to the pressure and B is subtracted from the value. So these are the only two changes you are able to observe in the perfect gas equation of the state. That is, A by V square term is added to the pressure and B is subtracted from the value. So why we have to add A by V square to the pressure and why we have to subtract this B from the value? That is very important. But that is why these changes are incorporated in the van der Waals equation of the state. So that is how it is basically governing the real gases behavior. That is very important one. So this why we have considered the A by V square term means here A means that is the attractive forces. That is, just now I told you that there are two important factors are there in the ideal gases. The first one is the forces of attraction or repulsion are neglected in the ideal gas, but in the real gases they have to be considered. So the A parameter is basically considering how many molecules are subjected to the forces of attraction and forces of repulsion. So this A parameter. So that's why the A by V square is basically considering the molecular forces of attraction and repulsion. Next, coming to the V minus B. So that is why we are subtracting from the value means. So I told you that each and individual molecule will occupy some amount of the value. But in the ideal gases, we are neglecting the volume occupied by the individual gas molecules as compared to the total volume of the system. But this is to be considered while studying the real gases. So that's why the A is nothing but is the forces of cohesion or repulsion. Forces of cohesion or repulsion. And B is nothing but is a co-value. That is, it is basically compensating the value which is occupied by the individual gaseous molecules. So the same thing we have written. So PV is equivalent to MRT, that is the ideal gas equation of the state. And here we are very important one, that most of the people are normally feeling that so PV is equivalent to MRT, where RE stands for it is a characteristic gas constant, but it is a universal gas constant. So what is the difference between the universal gas constant and characteristic gas constant? It is very important one. So here, whatever we are studying RU, that is the U stands for the universal gas constant. That is, this value is same for all the gases. So what is the value? That is the 8314 joules per kilomole Kelvin, or 8.314 kilojoules per kilomole Kelvin. That is the universal gas constant, which is constant for all the gases. But normally we are interested in R value, not RU. So R stands for the characteristic gas constant. That is, R is equivalent to RU by capital M. That is RU, universal gas constant, divided by molecular weight. Molecular weight here, capital M, it is a molecular weight. So RU by M. RU by M stands for R. So R is equivalent to RU by M. That is universal gas constant divided by molecular weight. Suppose I want to find out the what is the characteristic gas constant value of air. So then R is equivalent to RU by M. So RU is the standard, so 8314 joules per kilomole Kelvin. Then what is the molecular weight of the air? So molecular weight of the air is equivalent to 28.96. Normally we are taking it as a 29. So whenever 8314 divided by 29, so that value will give you, so what is the characteristic gas constant value of the air. So like that we can find out the R value for the various types of the gases. So same thing I have written here, R is equivalent to RU by M. So that is R value normally varies from one gas to another gas. So these are the important concepts which are related to the ideal gases as well as the real gases. Now let us see. So what were the previous questions which were appeared in the previous GATE examination? That is what we mean by the Boyle's law, Charles law and Gay-Lucas law. So Boyle's law says that is the three important parameters always we have to consider, that is the pressure, volume and temperature. So out of these three important properties, always we have to keep one property or one parameter should be constant. So whenever one parameter is constant, we are trying to find out the relationship between the remaining two variables. So that is there in the Boyle's law, Charles law and Gay-Lucas law. So Boyle's law says that, so whenever the temperature is constant, pressure is inversely proportional to the value. Pressure is inversely proportional to the value. So that's why PV is equivalent to constant, or P1 V1 is equivalent to P2 V2 is equivalent to constant. It is valid only under constant temperature conditions, that is the isothermal process. So that's why we can say Boyle's law is nothing but is a PV is equivalent to constant. Similarly, Charles law. So Charles law says that whenever the pressure is constant, volume is directly proportional to the temperature. Volume is directly proportional to the temperature when pressure is constant. So that's why V by T is equivalent to constant. So V1 by T1 is equivalent to V2 by T2 is equivalent to constant. That is the Charles law. So the next one is the Gay-Lucas law. So Gay-Lucas law says that whenever the volume is constant, that is whenever, so it's constant, so we are able to find out the relationship between the remaining two variables. So like that we are able to answer the Boyle's law, Charles law and Gay-Lucas law. So next one, for a perfect gas, so Cp and Cvr, that is the specific heat at the constant pressure and specific heat at the constant values are always is a constant. So like that the answer is A. So the next question is, which of the following is the correct statement of the Dalton's law of the partial pressures? So it is very important. That is the Dalton's law. That is the total partial pressure of the system is always equivalent to the summation of the individual partial pressures of the elements. That is, a P is equivalent to P1 plus P2 plus P3 plus P4, etc. So that is nothing but is a Dalton's law. So that is the pressure of a gaseous mixture is equivalent to the sum of the pressures each gas would exert if it is exerted alone at the mixture temperature and value. That is, P is equivalent to P1 plus P2 plus P3, like that. So an ideal gas is contained in a container which occupies a volume of 100 centimeter cube at 25 degrees centigrade and 1 atmosphere. The number of molecules of gas in the container are equivalent to. So previously just I shown you the slide, that is a 2.462 into the power of 21. So these are the number of molecules. So like that we can answer some of the important questions which are there according to the perfect gases and real gases. So the concept is very, very important. I hope you understood the concept very, very comfortably and very easily. So we will meet you once again in the next class. So thank you for attending and listening this class. Thank you very much.